Okay, now we are going to have the example 5.3, which is the last question we have for the tutorial for the size selection for the ball screw. In this example, we have a ball screw for a machine table. Drive is going to be selected. The axial force transmitted by this screw is 2.669 kilonewton or 600-pound force. And table is going to move for 609.6 millimeter or 24 inches per cycle. And expected to cycle for 10 times every hour for the design life of 10 years. Select the appropriate screw. So the first thing we have to do is we need to know how much the travel distance that this screw is going to be travel over the 10 years, where it's going to be doing 10 cycles every hour for 24 hours a day for 365 days a year for 10 years. So first, the number of the days is going to be 3,650 because this will be 10 multiplied by 365. We're going to multiply that by 24 hours a day. Then we're going to multiply by 10 times every hour and multiply by the distance of 609.6 millimeters or 24 inches if you want it to be in inches. So the first thing we are going to do is find the travel distance. And it's going to be something like 5.34 multiplied by 10 up to power 7 millimeters. You can calculate it in inches simply by dividing by 609, and then you are going to find, sorry, 609 to be divided by 25.4, and you will find this value in inches. Now we are going to go to the figure 17.8 for the ball screw. I'll do it in millimeters and again to do it in inches and find the answer. So we're going first to the table with the millimeters. So we said that the load we have is given as 2.67 kilonewton. That means is going to be somewhere in between here. And for my calculation is going to be somewhere in this position, 2.67 kilonewton. For the trouble life is 5.34 multiplied by 10 up to power 7. So you can see this is 1, 2, 3, 4, and 5. So it's going to be somewhere here. The intersection will be at that point. That means that my screw is going to be this line, the one above, and it's going to be 19.05 or the 3 over 4 of inches. And it's going to give me that the threads per by 25 millimeters or 1 inch is going to be equal to 2 threads, and the lead is going to be 12.7 millimeters. Now, if we're going to do it in the inches, the same distance is going to be 2.1 multiplied by 10 up to power 7 inches, okay, and 600 pounds force, and the intersection is going to be here, and I'm going to get the same diameter for the screw. Now, all done. Now let's go to do the rest of the calculations. So from the table here, at the 2.67 kilonewton, we can determine the ball screw to have a nominal diameter of 3/4 of the inches or 19.05 millimeters with 2 threads per 25 millimeters and lead of 12.7 millimeters. Now we can use these parameters to calculate the other stuff, like we can calculate the torque, we can calculate the speed, we can calculate the power, okay? And that's what we're going to do in the next example. So in this example, we need to find the torque, the power, and the life of the ball screw. So for the ball screw that we selected earlier, compute the torque required to drive the screw if a normal travel speed of the table is given as 4.23 millimeter every second or 10 inches in minute. And then we can compute the power required to drive the screw. So we start first with calculating the torque. You remember, the torque to raising the load is going to be 0.177 multiplied by the force multiplied by the load. Now, you know that the load, by the lead. So we know that the lead has been found to be 12.7 millimeters and the load was 2.67 kilonewton. So we can simply put that in the equation and the answer will be equal as 6 Newton meters. That's the torque. Now rotational speed can be calculated because we know how many threads we have in in one, sorry, we have two threads for every 25 millimeters, and we know that the total distance uh, is given already. So, and the L value to be 12.7. So we can put that in one equation to say that the omega is equal to one revolution, going to give me 12.7 millimeters. We have 254 millimeters per minute. And we know that the minute divided by 60 seconds multiplied by 2 pi. Okay, and this will give me the value for the omega to be equal to 2.094 radian per second. That's it. I can find the power by multiplying the torque by the omega. So 6 multiplied by 2.094 is going to give me the power of 12.566 watts. That's it. Now we can calculate actually the torque that's preventing the load from going down by multiply 0.1433 by the F multiplied by the L. Okay, so that's it. And we're going to have more